Okay, so we can define our magnification as just the image height over the object height. If that magnification is greater than 1, it's a bigger image than it is an object. If that magnification is negative, it's an inverted image. And then HI, if it's an inverted image, is negative. If it's an upright image, it's positive. We can also define the magnification based on the object and image distance, right? And it's going to look like this. The magnification will equal negative Q divided by P. That is the image distance, the negative of the image distance, the distance from the image to the mirror or lens, divided by the object distance. All right. Now for images in flat mirrors, the same rules are going to apply. But remember Q, actually I'm going to write it in the way that we wrote it before. No, this is right. Q is equal to negative P. All right. That rule applies for flat mirrors. Let me show you what that means actually. So here I am standing in front of the mirror, as I tend to do. I have a certain distance. I'm going to call this P, and then my image is right here, and this distance is Q. Now, it's a virtual image, so Q is going to have a negative value. My P is positive, but in order for Q to have a negative value, this has to be true, that Q is equal to the negative of my positive value for P. Now, if M is equal to negative Q divided by P, and Q is equal to negative P, that means that magnification is positive 1 for a flat mirror, which we know to be true, just, by experience. Now, when we're drawing the ray diagrams for a flat mirror, we should always remember the law of reflection. And the law of reflection, of course, says that the incident angle is equal to the reflected angle. All right, so let's say that we have this star, and it's in a mirror, and I want to know where does the image of the star exist. All right, I can draw a ray. That ray, actually here, let me, that ray originates at the star, and then it travels to the mirror, and then it reflects such that the incident angle here is equal to the reflected angle. Just look on the next page here. Now, if I want to find the location of the image, I'm going to draw two rays. Let's see. I'm sorry. I'm going to go back and do that on this page. No, I'll do it on this page. I'm sorry. So if I want to find where the image is, I'll draw my first ray. It's right there. Draw it by the law of reflection, just as we did before. These two angles are equal. Now, I'm going to also draw a second ray, because if I want to find out where the image is, then I'll need to find where two rays cross. I'm going to draw a second ray. I'm just going to draw it at a different angle. All right? And now this angle has to equal the reflected angle, so I'll draw it at a steeper angle. Now, if I trace these two rays back, I trace the reflected ray back, take a ruler and trace it back. If you're in the lab, you did this. Sort of curve there a little bit. Where these two rays cross is where my star is. Right? And then I can go and I can measure. This is my P value. This is my Q value. And if you've done this carefully, which I've done it okay here, if you've done it carefully, you'll find that P is equal to Q. I did this in lab, but you should recognize here that I found the location of my image by taking two rays and tracing them back. By the way, these rays are called virtual rays. They aren't real rays that you can touch and show on a screen or a piece of paper. Like I couldn't put a piece of paper here and show where these rays are going through space. They're virtual, but they still exist nonetheless in the space of the mirror to produce this virtual image. Here's a clicker question. or excuse me, an online quiz question. So where does person number 2 sees the rock right here? Person number 2 sees the rock right there. Where does person 1 see the image of the rock? So try that for yourself. And then also, what is the magnification of a flat mirror? We'll stop there and pick back up with spherical mirrors soon.